As you can see, I've skipped section 7 about power transfer. This section is there for your information. Section 8 is about grid converter PI control, and we'll start with the control of the DC bus voltage and the output of this single controller. So it's a scalar controller, will be a set point for the DC current. Of course, later on we're working with an AC current loop, so we have to transform this DC current set point into set points for the AC current loops, and this is done using a power balance. And then at the end we implement the AC current loops and the 3 currents of our 3 legs of the inverter. Okay, so we'll first consider DC bus voltage control. So remember that our inverter is connected to the grid, and that this is done through a filter, okay, and it's an LCL filter. Okay, so this is our grid tied inverter, and very often this inverter is connected through the DC bus to another inverter. Okay, and let's assume here that is a DC-DC inverter. Remember that we've seen this in the beginning of the course, and this is this energy management system, and that this leg here is connected to a solar panel. Okay, so there is power being produced. Okay, so there is a current that comes over here, and that's going to influence the DC bus voltage. Okay, so the DC bus cannot store all this energy, so it needs to be injected into the power grid. We only need a small current here in order to compensate the local losses, because remember, you have here this resistor that is in parallel because the capacitors are non-ideal. Okay, so if there is power being produced, the goal of this DC bus voltage controller is going to be to inject it into the grid. So let us assume that we have again this grid-tied inverter, and that it is now connected to another inverter that is connected to a motor. So to run the motor, if this motor is running in motor mode, you need to deliver power. Okay, so the job of the DC bus voltage controller will be to retrieve this power from the grid, and so the way it works is it's identical to what we had previously. If there is power delivered, well, you have a current that is outgoing, and what is going to happen is that the DC bus voltage is going to decrease. Well, this DC bus voltage controller will react by having power retrieved from the grid, and we will see how this works later on. But of course, it's this DC bus voltage controller in cascade with a current loop that will be implemented, and that will be explained later on in this video. Well, we are working on the DC side, so all signals will have a subscript DC. You have, of course, the voltage of the DC bus, which is available for measurement. And we have here a current IDC, which is defined positive in this direction. And this is consistent with what we had said for the inverter currents. They are positive when leaving the inverter. And this current is the sum of 2 currents. This current over here and this current over here. The top current here is an image of the power that is produced by, for instance, a generator, or the current that is delivered to a consumer. And if it can be measured, or if it can be computed from other measurements, well, it can be used as feed forward. Okay, this is why we have this superscript here, feed forward. The other current is used to maintain the DC bus voltage on set points, and this is done using feedback control. This is why this signal has a superscript feedback, FB for feedback. Let us now look at the feedback part. It's quite easy. The process can be described by this equation over here, and we have a minus sign over here because the current is in this direction, right? So the process is an integrating process where this is here the gain of the process. Well, to control the DC bus voltage, we can use a PI controller. Okay, so this is set point and this is the process value. The output MV, the manipulated value, will be this current over here. Okay, we know that the process is an integrating process, Kp over S. We know that Kp is the gain, it's minus 1 over the capacity of the bus. And now we can use the IMC tuning rules that we have presented before. We know that we should use an integrated time constant here. V stands for voltage loop here, which is 2 times the desired closed loop time constant for this voltage loop. Okay, later on we'll see that there is another constant like that, but it will be for the current loop. And then we know that the gain of the controller is 2 over Kp times this desired closed loop time constant. And if you take this quantity over here and you plug it in over here, indeed you have the gain of your voltage controller. Well, what have we learned so far? So the top part here is what you have implemented in exercise 2, and we have just seen that you can implement a voltage control for the DC bus voltage as follows. You use the PI controller and you use the following parameters, and they are derived from the IMC tuning rules. Okay, so this is the feedback part. If there is a current that is going to be injected on the DC bus, and if it can be derived directly by measurement or indirectly by computation, you should use it for feed forward. In our exercise, our simulation exercise, we do not have such a signal, so we can forget it. This signal over here is a DC current set point, but we're going to work with an inverter, and the current loop is going to be an AC current loop. So we have to find out how we can transform this DC set point into AC current set points. Remember that in some applications there is power that is produced and dumped on the DC bus. The DC bus controller will have to inject this power into the grid. In other applications there is power that is delivered to some application, for instance a motor, and this power is withdrawn from the DC bus. So the job of the DC bus controller is to retrieve power from the grid to compensate that. This is done by setting this current here IDC, but we know that we are working on the level of the inverter. Okay, so we are working on the AC side of the inverter, so somehow we have to transform this DC current set point in AC current set points, and this is going to be done by assuming a power balance. Okay, so we assume that we have a lossless system, which is of course not the case, but the losses are small in comparison with the power that is being transferred. And what you have is on one side the power on the DC side, this is what you've got here, and this is the power on the AC side that we have encountered before when we were modeling our DC bus. So assuming a lossless system, we have that the power on the DC side is the power on the AC side, right? So now if we use a Park transform, you can go to the DQ framework, and if we are using a power invariant Park transform, this means that it's a Park transform that is using this Concordia transform to go to the alpha beta domain before going to the DQ domain. You can write that the power in the ABC framework is exactly the same as the power in the DQ framework, written like this, right? If you would use this amplitude invariant Park transform, this is a Park transform that uses the Clark transformation to go to the alpha beta domain, you would have something similar, but you would have to introduce a factor 3/2 in the equation. Okay, we've seen in the previous slide that we have this equation with an additional term over here with the Q components. So remember that the PLL is tracking the reference angle of the grid voltage. So by definition we know that the Q component of the grid voltage is controlled to 0. Using things that are explained in section 7 that I've skipped, you can show that Vinf, so the inverter voltage, will be very close to the grid voltage. There will actually be a little phase shift, but very small. Well, so this is an approximation that we can make. So you can say that Vinf D component is approximately equal to the D component of the grid. And you can say something similar for the Q component, right? Okay, so if the Q component of the grid is controlled to 0, this means that this thing here will also be very small. So this is why we can forget about this term over here. And using this equation, we can isolate this D component of the inverter. Okay, it's simply taking this one divided by this one, and this is how we obtain this equation here. Here we know that the D component of the inverter voltage is approximately the same as the grid D component, and this is how we obtain this thing here over here. So we can use this equation here, okay, with E inf D, this one over here, to transform our DC set point into a set point for the inverter current. Okay, so you take the power on DC side and you divide by the D component of the grid, and this D component of the grid, for a grid coupling, you know what it is. It's by definition the Q component is 0, and we had seen that the D component was simply 230 volts times the square root of 2. So we had seen previously how you could control the DC bus voltage using a PI controller, and here you have the PI controller parameters. We have seen that in our application, in our simulation examples, you don't need any feed forward, and we had arrived here at a DC current set point that flows out of the PI controller, and this part over here is the power balance that I have just explained, right? So you take your DC current, you multiply by the DC voltage, so you have over here the DC power, and you can construct the D component of your inverter current by dividing by the D component of the grid voltage, right? So you could take your grid voltage D component from this signal over here, but don't forget that this is coming from the PLL, so it takes some time for the PLL to track the actual V grid. Okay, so there will be a transient, and during the transient this D component will not be correct, so I advise you to use 230 volt times the square root of 2 for this D component of the grid voltage. So I have now my D component for the inverter current, and by definition this D component is in phase with the voltage. Okay, this means that to control the DC bus we are exchanging active power. Okay, there is also here a E inverter Q component. Okay, I've set it to 0. I advise you to make a variable out of it in your simulation so that you can change it. Well, this current set point will actually ensure that there is current that is out of phase, 90 degrees out of phase with the grid voltage. So this will kind of influence the reactive power that is going to be exchanged with the grid, and reactive power will not have any influence on the DC bus voltage. So I've set 0 over here, but you can of course use any value of current. Of course you don't have to go above the limits of the inverter, right? And this will cause reactive power that will not influence the DC bus control. So you can use that to test your grid coupling. Okay, let's have a look at the AC current control. Remember that we work with a Park transform and that the dynamics are going to be affected. What you see over here is the equation that you expect. This is the relation that you have between current and voltage when you have a inductor, and this is the dynamics that you expect. But we've seen that because we were working with this rotating frame, you had an additional coupling term that is added, and this yields this equation over here. Okay, so we had obtained this equation over here. Okay, this thing here is something that you have to live with. It can be seen as a perturbation, right? It's the grid voltage, and this is this coupling effect. And this coupling effect, well, it makes the control a little bit more complicated. So this is the part where we have to be smart, and this is the part that we can control. So this part that we can control, we'll write it as the the sum of three things: something that you will control using feedback, a part where you do feed forward. I said there is a perturbation, you can measure it. Well, if you have a perturbation and you can measure it, you should try to, as much as possible, reject this perturbation using feed forward, and this coupling effect will try to reject as well using this decoupling term. Okay, so if you plug this one in here and you replace it in here, what will happen is that this term here will come and compensate this one, okay, and that this term over here, okay, since you divide by this thing over here, will come and compensate this coupling term. Okay, so using this equation where you have feedback control, feed forward and decoupling, you obtain a dynamic that is now very easy, and this is again the dynamic of a integrating process. So indeed you have an integrating process, there you have it, and it's a multivariable system. The input is in the DQ framework, it has two inputs, and the output is in the DQ framework as well, and you also have two inputs, and you can see because of the presence of the zeros over here, and this is because we have been smart previously and that we have decoupled the system, you can see indeed that there is no coupling effect. The gain is Kp here, and it's 1 over the sum of the two inductances. So what we'll do is use a multivariable PI controller. Okay, and if you go through the equations, well, you can see that you can simply use, because the system is decoupled, two PI controllers, one acting on the D component and the other one acting on the Q component. And instead of using two PI controllers, I'm going to use this vector PI controller that I have introduced previously. So there you have two options: either you use the one that you've created using during the digital control lab, or you design another one as explained previously in this series of videos. Well, we had seen that you can work with a PI controller, and of course we can again use our IMC tuning rules. Okay, remember that the process at a gain of 1 over L1 plus L2. Okay, so these IMC tuning rules say, well, choose as an integrated time constant 2 times the desired closed loop time constant, this time for the current loop. Okay, this is a design parameter, and then you had that the gain of the controller was 2 over Kp times this closed loop time constant here for the current loop. And if you put this one in here, indeed you obtain the parameters for the PI controller. Okay, and again this is here a design parameter. But don't forget that we have a cascaded solution. Okay, so the inner loop, the current loop, should be faster than the outer loop, which is the voltage loop. So we need to impose a condition on the two desired closed loop time constants, the one for the current and the one for the voltage. Okay, so it says it's larger than 5, and I would even advise to say that, well, TCLP for the current, you can take approximately 1 millisecond. Okay, and I would take the time constant for the voltage, which is approximately 20 times larger than the time constant for the current loop. Okay, so this is something you can experiment with, but this should be quite okay already. So what have we learned so far? So we've seen that over here in the exercise, well, you can set it to 0. Okay, this thing here, well, you can make it a variable and call it einf q set point, and then use it to experiment and to exchange reactive power with the grid. And this is the current loop that we have just introduced. Okay, so this is this vector PI controller. It's controlling the D and Q components of the inverter currents. Okay, here are the parameters. They were obtained using the IMC tuning. Okay, remember that there is a link between this desired closed loop time constant for the voltage loop and the one for the current loop. Okay, so this is the part of the inverter voltage that is set by feedback, and we had seen that there is also a part with feed forward. Okay, so here you need to go and take the perturbation, which is the grid voltage in DQ format, and add it over here. Okay, so that you use it for feed forward, and you have, remember, this coupling effect, and the idea was to use a term in order to decouple the system. Okay, and in that way the dynamics became a lot easier, so that you could use your PI controller and do as if the system was not coupled anymore. Okay, so these three terms, feed forward, feedback and decoupling, give you the voltage for the inverter, but it's still in DQ format. And then you need to do the inverse Bach transformation, and you need to go from DQ to ABC. And remember that we're going to use our extrapolation of the reference angle, taking into account that there is a, well, delay in the system, and this delay was approximately, let's say, 2 or 3 times TS. Okay, and this is our inverter voltage. In reality, what you need to do is to, well, transform this inverter voltage, as we have seen, into a duty cycle. In your simulation, you're not going to do that. You're going to use this directly and send it to the input of your model. In reality, in the background, there is this duty cycle that is being computed and that is sent to the actual system.